Hi, I'm Hollis Walker. Many call me Holly. I'm a concrete petrographer. I use microscopes, special sample preparation methods, and various kinds of equipment to determine the microstructure of concrete. I work at the Virginia Transportation Research Council in Charlottesville. This fine building houses the complete research effort of the department. We conduct all kinds of research on safety, traffic, purchasing, bridges, pavement, soils, and, of course, concrete. As you may know, I'm going to talk to you about some of the ways we examine concrete. We can determine the quality of the ingredients and the quality of the workmanship, and thus we can tell much about the construction history. We also try to assess the durability of the concrete in service. The specimens we deal with come from many different sources. Tests on specimens that come from current construction and maintenance projects have a rush priority. Specimens may be submitted because some unusual property requires an explanation. Low strength, early cracking, or perhaps a strange circumstance that prompted the inspector to insist on complete testing. Such circumstances include things such as screed breakdown, delayed finishing, form breakage, mixed contamination, and/or suspected cracking. When concrete deteriorates before its expected lifespan has elapsed, cores and/or fragments of the structure may be sent to us for evaluation. Specimens containing various experimental additives are often sent to us from the materials lab. Some of these require various types of petrographic analyses. Specially molded specimens in individual containers are subjected to 300 cycles of freezing and thawing. Internal deterioration is measured by determining change in the dynamic modulus. Surface deterioration is measured by weight loss and by assessment of the surface condition. Some of the specimens that are studied come from Research Council projects. In the study shown here, a bridge deck span is marked into squares to facilitate recording the condition of the deck and the logging in of the specimens taken. Many different types of data were recorded. Dry drilled specimens were taken for determination of the degree of chloride contamination. Each type of crack was recorded on the log map. And finally, core specimens were taken so that the absorption and permeability and the parameters of the air void system could be determined in the laboratory. When permeability is to be determined, a 2-inch thick section of a core is cut on this water-cooled diamond saw. These sections will be epoxied on the outside edge to make this edge impermeable. Then they are vacuum saturated with water and tested in this apparatus, which electronically measures the speed at which chloride ions penetrate the specimen. Chloride ions placed in one cell have to get through the concrete to the other cell to make the meter work. For all types of petrographic examination, including air void determination, smooth slabs of concrete are cut on this large auto-feed diamond edge saw. They are then lapped on this semi-automatic equipment. We have 2 of these laps, one for the coarse grit and one for the fine. The specimens are placed inside these rings, which are held by the idler wheels on the arms. The specimens turn freely inside, and then they move over the lap so the surface is evenly ground. Grinding compound and oil are added to the lap from this cup. It has a spiral down the center to pull material from the bottom of the cup. We lap the slabs not to a polished surface, but just until we can see the reflection of a distant light at a low angle. One of the most common examinations we do is a volumetric determination of the air void system. This is accomplished in our laboratory on a linear traverse device. The prepared specimen is mounted and leveled on the stage beneath this microscope. The stage is moved under the microscope by this motorized lathe bed. The speed of the motion is controlled with the left hand on this knob, and the operator is paying close attention to the features of the slab as it slowly passes under the crosshairs of the microscope. He is recording his observations by pushing and releasing the buttons under his right hand. Because I cannot show you what it looks like down the microscope of the linear traverse, we have arranged this demonstration. We had an art student working for us for 4 years running the linear traverse, and I asked her to make a black and white sketch of what concrete looks like down the linear traverse microscope, and this is what she produced. Then I asked her to draw a circle of the right size with her diagram with crosshairs in it to show you what it looks like down a microscope. And here now you're essentially looking down the microscope. There's the crosshairs. The microscope moves across the concrete, and as you hit an air void, you depress the air void button. On the other side, you let it up. Depress the button, let it up. That missed. Depress the button, let it up. Push the air void button, let it up. Now we need to run another traverse on this little piece of concrete. Here is the crosshair again in a different part of the concrete. It's moving across. Press the button, let it up. Press the button, let it up. Oh, a big ugly water void. Press the water void button. Let that button up. And here is an entrapped void, too large but round. Press the entrapped void button and let it up. And another traverse. The microscope is moving over the concrete. Approaches an air void, push the air void button down. Let it up. Push the button down, let it up. Push it down, let it up. And that's all the air voids on this traverse. It takes 100 real inches of traverse to make an air void determination and to allow the calculation of all the air void parameters. Now about the data that comes out of the real linear traverse. We can calculate not only the percent voids, but also the distance between the voids and the average size of the voids. The distance between the voids is called the spacing factor, and it's a very small measure. 0.008 is the maximum. The specific surface is the measure of the size of the voids, and it's a reciprocal number, and it should be larger than 500. In order to provide protection against freeze-thaw deterioration, the spacing factor should be under 0.008, and the specific surface should be over 500. I have here 3 specimens that are going to be passed among you with different percents of air. This one has only 1.5% air, way below the amount it should have. This specimen is within specifications. It has 5.6% air. On the other hand, this one, way out. It has been determined to have 17.3% air. Usually there are many questions to be answered about Portland cement concrete. I use this microscope and examine the features and use various reagents. and I compare what I see with what's in my memory of all the cement concretes I have seen throughout 22 years. Often, cracks and other features need various things in order to make them more visible, and I'll outline them with ink so that the slab might look like this. The ink in and on the cracks and the relationship of the cracks to the aggregate create different patterns for different types of deterioration. When we need to study the very fine microstructure in Portland cement concrete, we use this microscope. This is a fairly special microscope. It has two distinct forms of illumination. First, white light is produced in this housing back here and goes through the base of the microscope, comes up through the condenser to the specimen, where white light can be studied with all the features of an ordinary polarizing microscope. Secondly, we have ultraviolet light produced in this housing back here, coming through this collimating system to a little half-surface mirror in here, where it comes down to the specimen, creates fluorescence within the specimen where the epoxy has accumulated in voids and other structures, comes up, can be seen with the eyepiece, or if desired, the light can be sent up to the camera so we can take pictures. In order to be viewed with this microscope, concrete must be sectioned, mounted on glass, and polished thin enough to read through. These specimens will be passed among you for you to examine. Naturally, the preparation of such super thin specimens requires special techniques and procedures. A smooth surface is produced by grinding, and then the specimen is covered with fluorescent dyed epoxy and vacuum impregnated in this vacuum oven. A low heat and 2 days' time is required to cure the specimens to a grindable texture. The excess epoxy is cut away and the specimen is mounted on glass. Then it is mounted in this vacuum chuck and being cut down to about 1/2 millimeter thick with a diamond saw. The glass mounting gives it strength, and the cut produces a surface parallel to the glass. On this machine, the specimen is ground down with a diamond face cup until the concrete is about 3/100 of a millimeter thick. Then the specimen is mounted on this weight and placed on an oil diamond slurry on a silk-type surface. It is then allowed to move under the influence of vibration for 10-16 hours. When done, it is almost to the polished stage, and its thickness has been reduced to about 12 micrometers, about 1/4 the thickness of a human hair. There are 4 kinds of illumination available in this microscope, and we're going to look at each one of these separately. This is ordinary light. We're looking at a thin section of Portland cement concrete. This plain-looking area is actually all one grain of quartz that has some cracks and fissures in it. This is paste out here. Now each of these pictures are of exactly the same area. Here we have it with cross-polarized nickels. And we really don't gain any more information from this picture than we did from the earlier ones. We can see some highly crystallized material around here, but we really don't know anything more about the overall structure. The same is true of this pretty picture. It doesn't give us any more information. But with fluorescent light and the fluorescent dye impregnating the voids, we now can see what is paste, and there was crystalline material in this paste, and here is the quartz aggregate. But you'll notice in these cracks and fissures of the quartz aggregate, there are some areas that were filled in by the fluorescent dye. This dye fills in wherever there was a void or wherever there was a water pocket. So now with this specialized illumination, we can see what is empty and what is solid in this concrete. This is a thin section of very good concrete illuminated with plain polarized light. These large white areas that you see here, are really very small sand grains. These very spherical white areas are air voids. Now to look at it at slightly higher magnification, okay, and the little black specks in between in the paste are cement, some of which is hydrated and some of which is not. Now here we have it. Of course, it's been impregnated with a fluorescent dye, and here we have it in fluorescent illumination. And I want you to remember what this slide looks like, because we're going to contrast this with other concretes. This is a very good concrete. The sand grains are round, have relatively smooth edges, not a very shallow reentrant angles, and the aggregate is not very badly cracked. By contrast, look at this. This was made with sand from a different source. The sand has dirt on the edges. It's very sharp. It's not round. The entrant angles are deep. And they're all cracked up. Here is another view of this same slab of concrete with different sand grains in the picture. And with fluorescent light, you can see that the paste is no longer nice and smooth with the cement evenly distributed throughout the mass, but rather the water has collected around these very irregularly shaped pieces of aggregate, and the cement is left in bunches, unhydrated. Now, of course, these water-rich areas around the aggregate make zones of weakness, so the concrete is not as strong as if the cement was evenly distributed throughout the paste. Now here's a blow-up of the edge of one of those sand grains we just looked at. The clay edge you can see here. You may be interested to note this grain of hydrated cement down here. The rim around it is where it has been hydrated. The center has not been. Well, let's take a look at this edge of this sand grain. It has the dirty edge. Now you'll see that the fluorescent dye has actually impregnated that clay edge of that sand grain. Here we have a zone of weakness where the water content was high. And the cement is all congregated at a distance, mostly unhydrated, not doing any good, whereas the water is over here, making a weak place because the sand is so poor. This is a pretty good concrete. I show it to you so that you may see what the fluorescent light does to cracks and voids in concrete and how we can easily see them. This picture shows you a porous, weak piece of aggregate in the upper left, that big lath-like thing. Just wanted to show you how the fluorescent dye can get right inside an aggregate. Look at that. That yellow dye is all the way inside that piece of rotten feldspar aggregate. Of course, these big round circles down here are air voids. Now I want to talk about carbonation. You're going to have to think about this picture. Over here on the right-hand side of the screen is the top surface of this piece of concrete. This is air, essentially. Of course, that's the main thing you have to think about. Is on the right is air. This, of course, is a piece of aggregate. That's an air void, more aggregate, etc. Now we're looking at this with cross nickels, and we can see here's the air. Now this area, from the surface down inside the concrete, has become carbonated. That is, the calcium hydroxide has been changed to calcium carbonate, which is easily distinguished in cross-nickels because of its high birefringence. I mean, it's bright, isn't it? Down here, within the depth of the concrete, same amount of calcium hydroxide was present originally, but it did not become carbonated because the carbon dioxide that's required comes from the atmosphere. So it could only get that far down before it was all used up. Now in fluorescent light, you will notice, of course, that we've got the air space that was in this specimen preparation got filled with a fluorescent dye. The air voids got filled with a fluorescent dye. But the place that was so carbonated didn't get as much fluorescent dye as down in the body of the concrete. This means that the carbonated area is denser. Now that it's been carbonated, it doesn't let as much dye into it as does the uncarbonated cement paste. Now here is a different kind of carbonation, way down in the body of a core of concrete. Once again, you see this bright light, high birefringence, indicating calcium carbonate, which is where calcium hydroxide is combined with carbon dioxide from the atmosphere way down in the concrete to make calcium carbonate. Now with fluorescent light. Look at how much dye got into that carbonated area. It is just practically all open, which means that some carbonation is good in concrete, whereas other is bad. This is the bad type that makes the concrete loose and permeable. Now I want to show you this interesting picture. This is 50-year-old concrete, and right in the center we have an unhydrated grain of cement. Now over here on the left, over here on the right, we have a piece of cement that's about the size of what the cement we see in modern concrete. That would be big. But here we have this piece of cement in this ancient concrete. Well, they didn't grind their cement as fine then as they do now. Now let's look at this with cross-nickels. Oh, isn't that strange? The center is still unhydrated after 50 years. But we have this funny dark area around it. And then out here, we've got a bright area. I wonder what it looks like in fluorescent light. My goodness. The unhydrated part did not get any fluorescent dye in it. But this area that was dark is loaded with fluorescent dye. It's quite porous. It's my conclusion that the original cement grain was almost as big as this whole picture. In fact, you can see a little line around here. See this little line? That's actually the exterior of the cement grain. See it? Right around like that. Okay, whereas modern cement grain is smaller than this. That's quite a difference, isn't it? But interestingly enough, after 50 years, the center of this grain is not hydrated. It still has the power to add strength to the cement, to the concrete. Now about fly ash. This is a nice picture of a very good concrete that had fly ash added to it. Now you will note this fly ash particle in the center. It's round, it's hollow. Over here on the left, that's an air void. That's not fly ash. But this is fly ash. Up here, that's fly ash. Doesn't have a very big hole in the center. Sometimes fly ash is dark, but a good deal of the good stuff is light. Now this is a very good fly ash. You'll note there's very little carbon in this slide. There's a little piece of carbon in there. One little piece. That's very little for fly ash. Good fly ash. This fly ash is not so good. Right smack dab in the center, you'll see a great big piece of carbon. Notice how irregular the surface is. Now that means it's just like activated charcoal. the kind of charcoal that some people use in their fish tanks to filter out impurities in the water in the tank? Because organic compounds combine on the surface of such activated charcoal. This is activated carbon with a very active surface. Now, this isn't the only piece of carbon in this picture. You can see smaller ones, but the picture was taken because that had such a nice, clear, big one. Well, what happens is that the organic compounds, such as air entraining agent and Portland cement concrete, go and collect on the surface of this activated carbon. And once it's on the surface, it can't do its job in training air. So that is why we want a low carbon fly ash. And how do we tell whether it's low carbon or not? By how great the loss on ignition is, because this carbon can burn. So if it loses less weight when it's ignited, that means it has less carbon. This is the end of my presentation today. I hope I have made everything clear to you. Perhaps there are things I didn't cover that you want to know. Don't go away with questions still in your head. Ask one of the instructors, and they will try to answer them. If you have any problems with concrete that require my help, I'm right here at the Research Council. However, I cannot do anything with concrete that you have already tested for strength. I cannot reconstruct what a piece of concrete was like before you reduced it to rubble or even cracked it up. Thank you very much. I hope I've helped you.